Hello, everyone. This video contains the lecture that corresponds to what we would have done on March 31st, which is learn about what a chi-square analysis is. We typically do this exercise in class with M&Ms. All right, so if you got yourself some M&Ms, all right, as I suggested in my email, you can do this with real M&Ms. The worksheet is on Blackboard, so you can print the worksheet for yourself, or really all you need from the worksheet in terms of writing is this table over here on the second page. So you could also just reproduce this table by hand on a sheet of paper so that you can fill it in, and otherwise you can just follow along with my worksheet. If you were unable to get M&Ms, because I know times are dire right now, here is my bag of M&Ms. This is red and these over here are brown. It's a pretty dark photo, but you can use my M&Ms, all right, if you need to as we follow along in this video. Okay, the reason why we take this time to go through this example is because I've learned from previous semesters that while you guys learn about t-tests and correlation and possibly even regression or ANOVA in your business stats classes, you do not learn about chi-square tests, and we're going to need chi-square tests to analyze the data from our survey. All right, so we are going to introduce the concept of a chi-square test. We are going to calculate a chi-square statistic by hand during this video, but I am never again going to ask you to do that. All right, so we're going to do it by hand today to help you see the logic of what's happening sort of behind the scenes, how this chi-square statistic gets calculated and what it means, to hopefully help you understand the purpose of the test itself. And then in the next video, if you're watching in sequence, I will show you how to do this in SPSS, okay? So starting at the beginning, according to the Mars Company website, each package, excuse me, each package of plain M&Ms they sell should have the following percentages of each color of M&Ms, all right? So if they are doing what they are, wow, that was horrible. If they are doing what they are trying to do, all right, so if they're hitting their targets, this is the proportion of each color of M&M that will be in a bag. All right, and I don't know, to be honest, how they came up with these specific numbers. I'm guessing that there was some marketing research that found that this was the most appealing mix of colors. All right, but this is what is supposed to be in a bag. Now, in terms of what kind of data this is, right, if we want to try to tie this back to survey data, like the kind that we'll be looking at, you can think of this as each M&M's answer to a nominal response question. All right, so imagine that each M&M walks out of the M&M bag and answers this survey question: what color are you? Blue, orange, green, yellow, red, brown. In any given bag of M&Ms, this is the proportion of M&M respondents who should answer under each of these colors. All right, so this is a key thing about the chi-square test, is that we're using this chi-square test when we have a nominal measure whose response we're interested in. All right, so we've collected data on a nominal response scale, and now we're interested in learning something about how people answered that nominal response question. All right, so because Mars is trying to hit this target, this means that any given bag of plain M&Ms pulled from the shelves should have this distribution of colors. All right, so the sample, all right, any individual bag, any subset of the entire population of M&Ms should look pretty close to this distribution. All right, because you know, the Mars Company is manufacturing massive quantities of M&Ms, and then they mix them all up and filter them down into individual bags. And so if Mars is doing a good job, then not only should the giant vat of M&Ms at the manufacturing facility contain this proportion of these colors, but each individual bag should as well. All right, and so what we can do, what this chi-square test is going to allow us to do is it's going to help us determine, is the Mars Company doing a good job of hitting these targets? All right, so in other words, when we open our bag of M&Ms, are we seeing a color distribution that is pretty close to this distribution, all right, meaning that Mars probably is hitting its target? Or is what we're seeing in our bag so different from this distribution that it's unlikely to be the result just of chance and error, and instead it's reflecting some problem, all right? It's reflecting the fact that Mars is just not hitting their targets. All right, so in other words, if we were in class, what I would ask you is, when you open your bag of M&Ms, do you expect to see exactly 24% blue M&Ms in the bag? And the answer has to be no, because as we'll see when we start to fill out this table over here, we are not going to get these whole numbers, all right? Because we're going to have an unusual number of M&Ms in our bag, like 32, all right? And so having 10 out of 32 M&Ms, to have exactly 24% blue M&Ms would mean that we would need 5.2 blue M&Ms in a bag, and you can't have a fraction of an M&M in the bag. And so it's actually impossible for any individual bag of M&Ms to have exactly this distribution of colors. So we do expect to find some differences from this distribution. The question is, how big are the differences? All right, so remember what we talked about in the Intro to Inferential Statistics lecture. We know that what we find in this bag is not going to be exactly equal to what we're expecting, all right, this distribution up here that Mars is telling us about. And so the question is, are the differences pretty small, all right, suggesting that it's just a fluke of chance and sampling error. It's just reflecting the fact that we can't have fractions of M&Ms in a bag. And so it's as close as it could be, all right, but it's not really a big difference. Or are the differences so large that it seems unlikely to be a random occurrence, all right, suggesting that perhaps Mars's machinery is not producing colors in the proportions they'd like. All right, so we're going to look to see, given that we know we're going to find a difference, are the differences small enough that they can be attributed to chance and error? I think Mars is doing a fine job of hitting their targets. We're just seeing small differences. Or are the differences so large that it means that Mars must be doing something wrong? To do this test, we need what's called a chi-square goodness of fit test. All right, and this goodness of fit test, if you'll allow me to use improper English for a minute here, is asking how good does the distribution of answers in our sample fit this expected distribution that we learned from the Mars website. All right, so here's what we expect before we even open the bag. Does our sample fit this distribution well or not? All right, that's what this chi-square test is going to tell us. Did it hit this target or not? Ooh, hopefully I don't move that. Okay. All right, so before we conduct the test, we need to state our hypotheses. All right, our null hypothesis is that there is no difference. All right, with a chi-square goodness of fit test, these are always the null and alternative hypotheses. There is no difference between what we observed and what we expected. All right, so there's no difference between our observed color distribution in any individual bag and the expected color distribution set by Mars's manufacturing standards. And remember, this does not mean that we find absolutely zero differences. It means that the differences are pretty small, and as a result, we would conclude that those small differences are just due to chance and sampling error. Or the alternative hypothesis is that there is a difference between what we observed in our bag and what we expected from the Mars website. And this means that the difference that we're observing is too large to be just chance and sampling error. All right, I don't think this is a fluke just of this bag. I would expect any other bag off of the shelf to show similar differences as what I saw in my own bag. All right, so it's not unique to my sample. It's something that I would expect to replicate across lots of other samples. Right, there really is a meaningful difference. All right, so to test these hypotheses, to figure out which one of these hypotheses is more supported, we need to calculate the chi-square statistic. All right, and we're going to use this table down here to do that calculation. All right, so if you don't have any M&Ms, you can use mine over here. First step, wash your hands. You tired of hearing that yet? All right, the next step is to open your bag of M&Ms and carefully pour them out onto a sheet of paper. All right, if you have printed off this worksheet, there's a blank sheet on the back for you to tear off to pour your M&Ms onto. All right, do not eat any of the M&Ms for now. All right, you need to count them first. All right, so remember that the way we're thinking about this to try to equate this back to survey research is that, this M&M right here walks out of the bag and answers a survey question. Are you green, yellow, blue, red, brown, or orange? And so this one checks off yellow. All right, and so the question is, how many people checked off yellow? How many M&M people checked yellow? That's what we're going to enter into this observed row of the table. All right, what did we observe in our bag of M&Ms? All right, so I observed, let me see if I can get the text going. I observed, oh, this is going to be horrible. Let me just write with this thing. I observed 14 blue M&Ms, 7 orange M&Ms, 12 green, 13 yellow, 4 red, and 8 brown. And if I can pull up the calculator down here, the total number of M&Ms in my bag was then 58 M&Ms. All right, so I'll write 58 as my total over here. All right, I'm gonna get rid of this calculator and just do it on my phone so that I don't have to keep going back and forth here. All right, so we have our observed distribution. All right, these are the frequency. We've basically created a one-way frequency table here of the counts that we observed for each possible color in the bag of M&Ms. The next thing that needs to be done in order to calculate the statistic is we need to figure out what our expected values were. All right, and we can get rid of this picture of M&Ms now. And if you're at home, you can eat your M&Ms if you want. We get our expected counts from this expected distribution provided on the first page of the handout. All right, so if I have 58 total M&Ms in my bag and I expected 24% of them to be blue, then I'm going to multiply 58 times 0.24. All right, I'm finding out what 24% of 58 M&Ms is. And the result is 13.92. I need a stylus, guys. All right, so we can see just for the blue category, we have basically gotten as close as we possibly could to the expected value. All right, 14 is as close to 13.92 as we could have gotten. Let's see how well we do in the other categories. All right, 20% of 58 is 11.6. All right, now we start to see there's some differences here. All right, 7 is not that close to 11.6. We're seeing fewer orange M&Ms in my bag than we anticipated. We expected 16% to be green, so 58 times 16% is equal to 9.28. All right, so we got too many green. 14% of 58 is 8.12. All right, we got way too many yellows. 13% of 58 is 7.54. All right, so we didn't get enough red, and we expect the same proportion of brown, so this would be 7.54 over here again. So we did have the right number of brown, right? Given that we cannot have 7.54 M&Ms in a bag, 8 is as close as we could have gotten to that expected value. And to check your math here on this row, all right, when you're doing this, go out to 2 decimal places to keep your math correct. All right, if we add up all of the expected values on this row, 13.92 plus 11.6 plus 9.28, plus 8.12, plus 7.54, plus 7.54, you should get 58. All right, so we observed 58, and our expectations are based on having 58 M&Ms in a bag. All right, the next step is we are trying to figure out what we're getting to with this chi-square statistic is, were these two things equal to each other? All right, so is what I observed equal to what I expected? Did I observe what I was expecting? And so to figure out if I observed what I was expecting, we have to figure out how far off is what I observed from what I expected. And we start to do this in this first row by calculating the deviation observed minus expected. All right, so 14 minus 13.92 is 0.08. 7 minus 11.6 is negative 4.6. 12 minus 9.2, let me get my calculator out for this one. 12 minus 9.28 is, oh, the twos are so hard, 2.72. 13 minus 8.12 is 4.88. 4 minus 7.54 is negative 3.54. And 8 minus 7.54 is 0.46. Another check on your math. When you add all of the numbers in this row, you should get 0. All right, because 58 minus 58 is 0. Okay, so we're starting to see where the differences are here. Where you have very small numbers, like this 0.08, this 0.46, that's telling you that for those categories, what you observed was very close to what you expected. Where you see larger numbers, this is telling you where your differences were. All right, so I saw too few oranges, I saw too many yellows, all right, too few reds and too many greens. The next thing that we're going to do is we're going to square these deviations. The reason why we're doing this is to get rid of that negative sign. Still here, take it to 2 decimal places unless you need 3 to get a non-zero number. It's like here we need 0.006. This is 21.16. 7.40. 23.81. 7.08. And 0.21. In this row, there's really no need to add up these decimals. The sum right there would not be meaningful. All right, the last thing that we need to do in terms of calculating this chi-square statistic is we are going to standardize these deviations by the expected value. Let me hope that I can draw this in a way that makes some sense in this white space down at the bottom of this sheet. What we have so far are absolute deviations. All right, so in an absolute sense, how far away were we? We were 4 M&Ms away, or we were 2 M&Ms away. The problem with this is, let's imagine a situation where we expected to see 95 of something, all right? We expected 95 people to answer a question one way, or in a second situation, we expected 5 people to answer something in one way. And what we observed in one case was here we observed 100 when we expected 95, and here we observed 10 when we expected 5. In both of these cases, the deviation is 5. All right, so in both cases, we were 5 away from what we expected, but in one of these cases, that deviation of 5 is worse. All right, it represents being more off. All right, and so in this case, we were only off by a little less than 5%. All right, so we wanted 95, we observed 100, we were roughly 5% off. Here we observed, oh wow, here we observed twice as many as we were expecting. All right, so here a deviation of 5 represents a very small difference between what we observed and what we expected, all right, relative to that expectation. Here, a deviation of 5 represents a very large deviation, right? We got twice as many as we were expecting. And so it's important that we standardize these deviations to be in relation to what we expected. How big was this deviation? All right, and so let me erase this stuff down here. What we are going to do is we are going to take the number in the deviation row and divide it by the number in the expectation row. Okay, so here I would do, I know that the cursor handwriting is terrible, 0.006 divided by 13.92. Oh, we have a lot of zeros here. 0.0004. All right, 21.16 divided by 11.6 is 1.82. All right, and we're going to continue this across the row. 7.4 divided by 9.28 is 0.80. 23.81 divided by 8.12 is 2.93. 7.08 divided by 7.54 is 0.94, and 0.21 divided by 7.54 equals 0.03. All right, so here we can see sort of, how this kind of shakes out. In both of these cases, the orange column and the yellow column, we had a deviation of roughly 4.6. They were pretty close to each other here. And so while in an objective sense, we were off by a little over 4.5 in each of these cases, 4.5 is not as bad of a deviation when we were expecting 11.6 versus when we were expecting only 8.12. All right, so here our standardized deviation is a larger number, reflecting that the amount that we were off is greater in this yellow case where our expectations were to see a smaller number than over here when our expectations were to see a larger number. All right, so to calculate our chi-square statistic, we are going to add the numbers across this row. Give me just a second to do that. And this adds up to 6.52. All right, or you can write that in this box down here. 6.52 is our chi-square statistic. All right, so what this number is, the chi-square statistic, so we can remember this later when we're just letting SPSS churn out these chi-square statistics for us. The chi-square statistic is a single number that summarizes the magnitude of the differences between the observed distribution and the expected distribution. All right, so importantly, it's not telling us just blue observed versus blue expected. It's telling us the entire range of possible nominal response options. How different was the distribution that we observed? All right, the distribution referring to all of the counts that we observed for each possible nominal response option. How different is the distribution that we observed from the distribution that we expected? A larger chi-square number means there were a lot of differences. A smaller chi-square number means that there were no differences. At its minimum, chi-square can be equal to 0. All right, if what you observed was exactly equal to what you expected, then you would have 0 deviations, 0 squared deviations, and this row would also be 0, and you would end up with a chi-square statistic of 0. As chi-square gets larger and larger, that indicates larger and larger differences between what you observed and what you expected. All right, the question at this point is, oh, wow. All right, so let's keep in mind 6.52, because apparently I have to erase this in order to scroll down to the next page. All right, 6.52, are we all remembering? I'll write it on the next page. All right, so the question is, how big of a difference is 6.52? All right, let me write this again over here. 6.52. All right, remember that our null hypothesis does not say that the chi-square statistic has to be 0, all right, in order to favor the null hypothesis. The null hypothesis just says that the chi-square statistic, the differences would have to be small enough that statistically it's likely for them to have occurred due just to chance and sampling error. All right, so to find out which is more likely, all right? Is it more likely that we found this big of a difference because of chance and sampling error, or is this difference so large that it's unlikely to have occurred due to chance and sampling error, and instead I think it's reflecting a population level difference, where at the population size, all right, all of the M&Ms that Mars is manufacturing, they're messing the colors up, all right? They're not hitting their distribution. We have to figure out what our p-value is. In SPSS, when we ask SPSS to do this, SPSS will spit out the exact chi-square statistic and the exact p-value for us. So I'm going to show you how to look this up in this table, but you're not ever going to have to do it again. All right. When we look up a p-value for a chi-square test, we need to know our chi-square statistic, and we also need to know how many degrees of freedom we have. The reason why this is important, if we scroll back up here for just a second, remember when we were calculating this chi-square statistic, that in each of these boxes we had some non-zero number, all right, because we were not going to see exactly what we were expecting. And what this means is that when you have a nominal response scale measure that has lots and lots of options, you are going to be adding up lots and lots of non-zero deviations for all of those different options that people could have circled on the nominal response scale. And so that means that if you're observing, if you're comparing an observed distribution against an expected distribution, if there were only two categories, you would naturally expect this chi-square statistic to be smaller than a chi-square statistic that was based on, for example, here, 4 categories. All right, this chi-square statistic is going to be larger just because there are more numbers getting added up here. Even if they were all very small, this one would be larger because there's more numbers getting added together. All right, so when we consider how large our chi-square statistic is, we have to take into account not only what is the actual chi-square statistic, but also how many categories got added together to create that chi-square statistic. All right, and so that information is captured in what is called the degrees of freedom here. All right, and for a chi-square test, the degrees of freedom are equal to the number of response categories in your nominal measure minus 1. All right, so in our M&M data, there were 6 possible color categories that an M&M could have circled when it took the survey. All right, so our degrees of freedom are equal to 6 minus 1 or 5. All right, and so just knowing that 5 is important when we come down to this table. All right, so in this table, what's happening here? We have 5 degrees of freedom in our measurement, all right, because we had 6 categories. So we're only interested in this very bottom row of the table. And inside this table are possible calculated values of chi-square. And at the top in the header, we have the p-values that correspond to those levels of chi-square. All right, so my chi-square statistic is closest to this number. If you got your own bag of M&Ms and you calculated a different chi-square statistic, it is unlikely that you will find your exact chi-square statistic down here in this row. All right, there's obviously not enough space for me to print the chi-square statistic for every possible p-value. Instead, you just need to find the number that's closest, all right, or figure out where in between these columns your chi-square statistic would fall. Because my chi-square statistic is very, very close to 6.63, I am just going to write, for the sake of brevity, that my p-value is equal to 0.25. What this p-value means is that there is a 25% chance that I would find a chi-square statistic this large or larger due only to chance or sampling error. All right, so there's a pretty good chance that I would find differences of this magnitude due just to chance and sampling error. All right, and because my p-value is so large, all right, p is equal to 0.25, remember if p is less than 0.05, we are going to reject. I think the writing in this is worse than the writing in PowerPoint. We're going to reject the null. And if p is greater than 0.05, we are going to, I'm just going to write fail to reject the null. All right, so in our case, in my example, my p-value is greater than 0.05, so I'm going to fail to reject the null hypothesis, which means that I'm concluding that what I observed is equal to what I expected. All right. And I know that this hurts because what we observed is not equal to what we expected. But remember that implied in this null hypothesis is that while we observe differences, we are concluding that those differences were not real in the sense that they don't reflect actual population level differences. All right. So basically, we're concluding that the differences that we found are just a fluke of our sample. If we had opened a different bag of M&Ms, we don't think that we would have found these same differences. If we could conduct a census of all of the M&Ms that Mars manufactured this year, we don't think that we would find differences. All right, we would think that Mars was hitting its targets just fine. All right, so in other words, the differences that we observed in this bag of M&Ms are not big enough. All right, they are not strong enough evidence to conclude that Mars is not hitting its target. It's some evidence. All right, it's a little bit of evidence, but it's not strong enough. All right, and so because it's not strong enough evidence, we fail to reject the null hypothesis, and we conclude at the population level, I don't think that there are any real differences. In order to reject the null, all right, if you guys have your own bags of M&Ms, you would need a p-value of less than 0.05, all right, which means that you would need a chi-square statistic of 11.07 or larger. This is the magic number in this specific case where if your differences resulted in a chi-square statistic of 11.07, at that point, the differences are large enough to conclude that Mars is doing something wrong. All right, here the evidence now would then be strong enough to draw that conclusion, to have a p-value of less than 0.05 and to reject the null. When we do this in class, everyone has their own bag of M&Ms. I ask for a show of hands of how many people rejected the null and how many people failed to reject the null. And typically what happens is that only about 3 or 4 people in any classroom, all right, will raise their hand. And that those 3 or 4 people correspond to people, that's our error rate. All right, those are people who rejected the null. Their specific sample showed that they should have rejected the null, but they shouldn't. All right, they got a false positive. All right, and that's that error rate in action. Remember that P of 0.05 means that there is still a 5% chance that you're wrong. All right, and so those 3 or 4 people who raise their hand, they are in that 5% chance of being wrong. They are actually wrong. All right, and they're being wrong at about a 5% rate. All right, when we look at the total number of hands that are raised versus the class size. All right, so this is the chi-square goodness of fit test. Let me erase some of this so I can see if I can write one more thing on the blank page on the next, if I scroll down a little bit. I am aware that this is, I'm just going to use this as a blank sheet of paper. I'm aware that this M&Ms thing is it's an unusual example. Where this gets used in practice, all right, and where this is definitely going to get used on your data analysis plan when you work on it is, I'm not going to be able to come up with a number. I'm trying to see if I can reference one of your papers over here. Let's say that another survey was conducted of students and it asked them, have you ever taken ADHD medication without a prescription? And let's just say, I don't remember what the numbers are, but let's just say that 25% of students in that survey said yes, and 75% said no. All right, and this is data from a survey taken at another university. All right, so these are just students somewhere else. All right, and so we can ask this question. The students that we observe at Ole Miss, all right, the people who answered the survey for you, they also answered this question. Have you ever taken an ADHD prescription, prescription without a valid prescription from a doctor? We are going to observe some proportion of yeses and some proportion of nos, and we can ask, is what we observed at Ole Miss equal to what we expected based on what has been found at other universities? So in other words, are Ole Miss students like these students at other universities with respect to how many of them have taken these ADHD prescriptions, or are they different? All right, are the numbers here going to be pretty close to this, or are they going to be so different that we conclude Ole Miss students at the population level, not just the people inside my sample, but at the population level, I think that Ole Miss students must really be using these drugs at a higher or lower rate, depending on the answers that we end up seeing here. All right, so one way that this chi-square goodness of fit test gets used is to compare the population from which your sample was drawn against some external reference point. All right, so you get numbers from some other study, all right, or there's some guideline about how people should answer a question. And we want to know, is our population equal to that external reference point with respect to how they answered some nominal scaled measure? Another way that it gets used is, let's imagine that, I'll use the example from the ADHD thing. We ask about, I'm not going to be able to remember all the drug names. It asks, which of these drugs have you taken? It's like Vyvanse, Ritalin, I don't know, something else and something else. You guys know this stuff better than me. All right, let's just say drug A and drug B. And we ask this question on the survey, which of these have you tried before? If all of the drugs were equally popular, we would expect 25% of students to say that these are the drugs that they've used, right? Because if all of the drugs are equally popular, then they should all be selected equally often by students, all right? So they're sort of randomly distributed across the population, and a quarter of people are taking Vyvanse, and a quarter of people are taking Ritalin, and a quarter are taking drug A, and a quarter are taking drug B. But if one drug is more popular than the others, all right, let's say Vyvanse, because that's one that I hear you guys talking about a lot, then we should see a number much larger than 25% here, all right? Maybe 60% of students in our sample say that they take Vyvanse instead of the other ones. And so we can ask this question, are all of the drugs equally popular, all right? Meaning we would expect to see 25% of people circling each of these four options, or are we observing a distribution that is different from equally popular? All right, suggesting that one drug is more popular than the others. All right, and so if we did this and we found a chi-square statistic that was large and a p-value that was small, we would look back at this and say, okay, there are differences. We are not observing equal preference across these four drugs, and we might look at this and say, there's the culprit. All right, that's where it's not equal. People prefer Vyvanse, much more than they prefer the other drugs. All right, so this is another way that this chi-square test gets used. Fundamentally, I think that what is helpful when doing the data analysis plan, all right, and we'll be able to practice this more in the next video about how to do these tests in SPSS, and we'll have more examples. But we need to remember that what this test is asking to do fundamentally is there is an expected distribution of numbers, all right? People answered some question on a nominal response scale. They could have circled option A, option B, option C. We want to know, is what we observed equal to some specific distribution that we expected, either because we have some external reference point that we want to compare our population to, or we just have a pattern like equally popular, so 33.3, 33.3, 33.3. Is what we observed equal to that expected distribution or not? All right, we have one variable from our data set. It was measured on a nominal response scale. We are comparing the pattern of answers on this one variable against some predefined pattern. All right, this is what the chi-square goodness of fit test is doing. One nominal measure compared against a pre-specified pattern. Do these two things equal each other, or are the patterns different? That's what the chi-square test is doing. In the video that corresponds to April 2nd on the syllabus, I will show you guys one more chi-square test whose math is very similar, whose interpretation is very similar, but it takes an additional step, all right, and does one more thing. But we will get to that in the next video. Today, I thank you for coming and listening to this video. Enjoy your M&Ms. If someone bought some for you, wash your hands. I hope you guys are staying inside and staying safe. Bye.